questions. This is something which makes the class closer to some real interaction, as if you were here. And with your section, I've been very happy so far. Okay, so today we're going to cover some relatively new material. And this new material, after the rank and the range that we covered the last time, we're going to talk about the vector spaces. Vector spaces, it's a set, it's a non-empty set composed of vectors that have few properties, okay? With these few properties, we're going to see what these properties are. Just give me 1 second to find out where I have the... Okay, I got it. So this is week 6 material. So we will talk about vector spaces. For vector spaces, what they are, let's call it real vector space V is non-empty set which has or equipped with addition operation and scalar multiplication. Equipped with addition and scalar operation. So this is a vector space, and the vector spaces, the definitions, they will go like this. In a few definitions that we are going to provide, because I need to use this space, we are going to assume that we have a vector V and the vector W, which are elements of the vector space V, and then we're going to have constants such as alpha and beta, which are just simple real numbers. These are constants. And then common question that comes when we discuss about vector spaces. First of all, it is very useful to understand how the sets are related, or what makes a vector space a subspace of another space. And the understanding of the vector spaces, it is very helpful, and you can find it useful in many different future courses that you might take during your study program. And to be a vector space, we need 10 properties. So there are 10 properties. It's not that you don't need to memorize them all one by one, because almost half of them, they are very intuitive, okay, or something that you might expect. Let's list these 10 properties. So to be a vector space, the first one is that we have the following. For any U, and what did I write? V and W. Let's use V and W. So for V and W, which are members of the vector space, or elements of the vector space, V plus W should be also in the vector space. So closer, this is called closed under addition. So when we add two vectors, we wish that these two vectors are still in the space. So we don't want to add two vectors and then we get a vector which is not described, or which does not have the same property of the vector space. That's the first one. The other one, it's V plus W. And I want you, because I'm going to ask you in a few minutes, I want you to figure out which one of these 10 properties that we're going to write. We're going to write 10 of these. Which one of these you already know? Okay. So this one should be equal to W plus V. So let me ask you this. Would you expect such a property? This is commutative law. So have you ever seen this before? If you have two matrices, A plus B, would this always be equal to B plus A?
Yes.
Yes. So assume that you already know this. Okay. This is not something you need to memorize. Matrices, you add them, they are commutative, so you don't have to worry much. Now, we have another property here, which this also could be intuitive, or you might expect this, which means that you don't need to memorize this one. This would be equal to U plus V plus W. This is another property. The fourth property is that the 0 plus V, this should be equal to V again. And then the next property is the following. So V plus W, this is equal to 0. So what do we learn from these two properties? We learn that 0 vector should be in the vector space V, okay? And also, it looks like we should have that V should be equal to minus V. So the negative of a vector should be in the same vector space. These are the first 5 properties. The sixth one is the following. So if we multiply any vector V, we expect the scalar multiplication of a vector to be still in the vector space. The seventh property is the following. We have alpha times V plus W. This should be equal to alpha V plus alpha W. This is also almost intuitive. We might expect this. And then the eighth property would be the following. This alpha plus beta times V. This is equal to alpha V plus beta V. Then the ninth is that this is also something not very challenging. This is alpha times beta V. This would be equal to beta alpha V. Okay. The commutation of multiplication is the same. Like 3 times 6 is equal to 6 times 3. And the last property is the following. Where we have the 1 times V. This is equal to V. Now, you have a look at all of these properties, and I believe that the only new properties which need a little bit of new insight are 1, 4, 5, and 6. 1, 4, 5, and 6. Okay. So, what does 1 say? 1, it checks whether the vector space is closed under addition, which means we add 2 components. Are we still in the vector space? What is 4? 4, in essence, is just searching for whether the 0 is a member of the vector space. Now, the 4 and the 5, they are very close to each other. They are almost the same statement, but stated differently. Which, in principle, 4 and 5, you are really searching for this. Is the 0 an element of the vector space? Now, let's give an example right away. So let me ask you this. If you have an equation of 3x minus y plus 2z, I need to give this equation so that we just pick up with the previous information. If this is equal to 2, I want to ask, what is this equation? This is an equation of what? What could this be?
A plane.
Correct. This is a plane, okay? And this is a plane, and this is a non-empty set because we can find an infinite number of triplets or combination of x, y, z which satisfy this condition. Now let me ask you this: does this plane include the 0?
No.
No, that is correct. So it looks like this plane is not a subspace of R cube. Okay, so this is a plane. Let me write this like a P. The question is that could this be a subspace of R cube? Why R cube? Because the vector that we're analyzing, it is x, y, and z. Okay, and we want to see whether the 0 satisfies this condition. You said no. Okay. Why? Because if you do 3 times 0 minus 0 plus 2 times 0 is equal to 0, it's never equal to 2. So this is a plane, a good looking plane, but it's shifted from the 0, 0, 0 point. What about this equation? What does this look like? Plus 2z, this is equal to 0. What can you say about this plane? Does this include the 0?
Yes.
Yes. So we can answer here, this is no, this is a yes. So this is what we mean here. It's not something which we never saw it before. Okay, so we can pick up with the previous information that we have had on the properties of vectors or what we understand for the planes. Okay, then, so 4 and 5, this is what we're really checking for. What is 6? 6 is checking whether the vector space is closed under the multiplication with a scalar. So we have these three in principle. We don't need to check all 10 different properties. It's always good to check to go over those. But we're just talking about the situation that let's try to minimize as less as possible. In principle, you're not even, what did I say? Let's try to memorize as less as possible. So this one, all of us, we should know. Okay, vector space is a non-empty set equipped with addition. Okay, we add vectors, and then we multiply them, scalar multiplication. We don't want to multiply two vectors with each other. That could only be the dot product. We want to have linear algebra. Linear algebra is not including x squared, y cubed. We don't have these kind of terms. We want to keep all the parameters as to the power of 1. But we're going to have multiplication to some degree, but only multiplication with a scalar. So in principle, what we are looking, all this, so if you have 10 statements here, okay, so we have 10 statements, right? Okay, good. To check whether it's a vector space, everything in fact is written right here. It's written here. Actually, the 0, so we want addition, which is statement 1. We want scalar multiplication, which is statement 6. And it should be non-empty, but actually it's not the 0. This is actually not clearly defined. So 0 should be an element of vector space. Now, let me ask you one question. Is this vector space V1, is this equal to a set composed only of the vector space 0? Is this a vector space? What do you think, yes or no? Let's check property 1. So we have only the vector 0. So what we can do is the following. We do 0 plus 0, so 0 is another vector in the vector space. Is this the vector space? Yes. Then we check for the fourth option. If we do 0 vector plus a 0 vector, which is the only vector component of this vector space, is this still V? The second one is also confirmed. What about this? V plus W is equal to 0. So can we find the vector W, which is the negative of the V? Yes, because minus 0 is equal to 0. Okay, so we found the negative vector. So this is also satisfied. What about alpha times 0? Is this an element of vector space? Yes, because it's still 0. So it looks like this vector space, which is non-empty because it has only the 0 vector. This is a vector space in itself. Okay. Let's look for another vector space which can be defined like this. Let's try that. We can have a vector space W. So we have a vector space W, which is equal to a triplet of numbers x, y, and 0, such that x and y, they are real numbers. X, y, they are real numbers. Okay. So is this a vector space? What do you think? What can you say for this vector? So x and y, they are element of R space. So what is the first condition? The first condition is the following. If we have two vectors, x1, if we have this initial vector, then we add x2, y2, 0. What do we get? x1 plus x2, y1 plus y2, and 0. Is this, so we added, is this a vector which belongs to vector space W? Yes, because x1 plus, right, would you agree? So we could agree because x1 plus x2 is still a real number. y1 plus y2 is still a real number, 0 is 0. So it's like we have a vector where the third component is always 0. Then we can check whether the negative of these numbers exist. We have here x1, y1, plus, can we find a minus x1? Yes, we can. If this x and y was defined such as, so let's consider another vector space. This is another example. Sorry for jumping to this side, but that part of the board is full. So we could also define a vector space x, y, and 0 such that x, y are numbers of real numbers, but positive numbers. Okay? If this was the case, then we don't have a vector space here in this case, because we cannot find a negative vector such that one vector plus another, we get a 0. But here we can. So here we can have minus x1, minus y1, and this would be equal to the 0, 0, 0, which means that this is the 0 vector, and the 0 vector is an element of the vector space W. Since x and y, they are any real number with no constraint, this would be 0, 0, right? So the 0 vector is already in here. When you come here to this new vector space, for any triplet of numbers, which is x1, y1, 0. As an example, this could be equal to, assume 3, 2, 0. We cannot find, we have to do the following, 3, 2, 0, plus minus 3, minus 2, 0. This would be equal to 0, 0, 0. But the second element, it is not in W1. This is minus 3, minus 2, 0. So, W1, not a subspace of R cubed. But here the W, this is, we can answer, is subspace of R cubed. Okay, so this is how we try to analyze whether something has a Let's see another example. Let's assume we have a set S1, which is defined as a triplet of number x, x squared, and 0, such that x is an element of real numbers. Okay? And the question is the following. Is S1 subspace of R cubed? This is the question. How can we answer this? The first thing that we do ask is the following. Let's have for x equal to a. What is the value? This is a squared 0. For x equal to b, what is the vector? It is b squared and another 0. Yes. So what would be the addition of these two vectors? Because this is an element of S1. And this one is also an element of S1. The question is the addition of these two an element of S1? So if we add them, we would get a plus b, a squared plus b squared and 0. Now the question is this element? This is the question. Is this element in S1? What do you think? Or maybe we can write it like this. answer this. Is the summation of these two vectors in S1? Yes or no?
No.
No. Why?
Because of a square.
Because the second entry is not the square of the first one. Because an element of S1 would be the following: a plus b, and the other element it would be a squared plus 2ab plus b squared and 0. Any number that looks like this would be an element of S1. Okay, but in here we observe that this is not the case. Okay, so we say that is S1 subspace of R3? We just say no. Here, let's see another example where we have S2 is equal to x, 2x, and 0. X, 2x, and 0, such that x is any real number, R. Okay? So we can first check addition. Check addition, whether the subspace is closed under addition. How do we do it? We can set A, 2A, and 0 plus B, 2B, and 0. And what is the answer going to be? The answer is A plus B and 2 times A plus B. So this is and 0. So is this an element of this space? Yes. So the first one it is satisfied. The second one is what do we check? I believe we check whether actually we can do the 4 and 5. We just see whether the 0 is an element here. Now x, it can be equal to 0 since x is given that is any real number. So if this is the case, then we can imply that the vector x, which is equal to 0, 0, 0, this would be an element of S2. The final statement is the following, or not the final statement, the final step that we need to check for, and just allow me again. So what was property 4? I think it was 0 plus v. This would be equal to v again. Or we'll also have this, it does a w. Can we have a w where we add it with v and we get a 0? So with this statement, we're checking these two, which means that can we construct a negative v here? Yes, we can, because we can put a to a 0 minus a minus 2a 0, so we can have that. But now we check the last property, which was the following: is alpha times v an element of W, sorry, S2? So this is what we ask next, and we start here alpha A and alpha times 2A. Well, let's do it like this better. So we don't do it, let's state it like this. So we have alpha times A, 2A, and 0. And this would be equal to alpha A, alpha times 2A, and 0. And this would be alpha A. Then we get here 2 alpha A. Why? Because alpha and 2, they can interchange the places. So as a result, what do we observe? We observe the first number, and the second element is the first number times 2, so which is like this. So then we can say that this is an element of S2. So from here, we see two examples where S1, it was not a subspace of R3, which was simply controlled because it was not closed under addition. Then we saw another case where it was closed under addition. Now, and the answer here it was no. as in here. And for the second case is that is S2 an element of S3? We can say that S2, so not element, is subspace of R3. Why are we asking whether it is a subspace of R3? Because we need a triplet of numbers to constitute or to compose this vector of ours. Now, let's see a couple of more examples. If we have a vector space A11, A12, A13, A21, A22, and A23, A33, what is this matrix? We can ask. This matrix is a 3 by 3 matrix. This is 3, 1. So let's call this one matrix A. Okay, I just want to use some names. What can you say about the matrix not B? Let's call this one matrix L. This is A11, 0, 0, A21, A22, 0, A31, A32, A33. What is this matrix? This is the lower triangular matrix. Now, the question is the following. Is the matrix L a subspace of matrix A? So if A constitutes a set, a non-zero set, which includes all the 3 by 3 matrices, can the L, or is L a subset of A? What do you think? What can we say here? So, and then we can also look at diagonal matrices D, which can be equal to A11, 0, 0, 0, 0, 0, 0, A33, and this is A22. So this is the diagonal matrix. And then we can have also identity matrix, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. We can also have a zero matrix, which is 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so can you answer the first question? Is L, which is a lower triangular matrix, what is a lower triangular matrix defined as? This is defined as having all the numbers above the diagonal, or all the entries above the diagonal equal to 0. So here, we could say that L as a vector space, this is the subset of A. Would you agree with this? And similarly, we can also that U, it is a subspace of A. Okay? And then we could also report the following. What can you say about the diagonal? This diagonal, is it a subspace of what? Can I have some input from you?
Is a subset of A, L, and W.
And U.
Yeah.
Okay, so diagonal matrices, yeah, thank you. Diagonal matrices, they are a subset of, let me write, actually, yeah, I can write all of them, but we might misunderstand this one. So this is a subset of L, D is also a subset of U, and many more. And also, identity matrix, this is a subset of D. Why? Because identity matrix has all the diagonal terms, all terms are 0, but these values are specifically equal to 1. Okay? What about for zero matrix? Is the zero matrix a subset of identity matrix? What can you say about this?
No.
No, that's true. No. Why? Because identity matrix wants here, but this wants zeros. But is the zero a subset of diagonal matrices?
Yes.
Yes, that's true. Is the zero a subset of L? Okay, yes, we can answer this as a possible yes. Okay, so these are some examples of how we can, wait a second, okay. Of how we define the subspaces of a specific So if we have two lines which are described by these equations, are these subsets of R squared? What can you say? So y equal to 2x, we have a space which is S, which is xy, such that y is equal to 2x. This is how we relate this, and x is any real number. This is S. And the U would be a vector space which is composed of x and y, such that y is equal to 2x plus 1. So we are listing the conditions, and x is any real number. So the question is the following: is S subspace of R squared? That's a valid question. What do you think? So let's pick two vectors from S, 1, 2, and 3, 6. Let's add them together. We get 4 and 8. Is 4 and 8 an element of the S?
Yes.
Yes, that's true. So yes, the first condition is satisfied. And then, is the 0, 0 an element of S? Yes. Which means, or does the S include the 0? Yes. So this is also a second yes. Then the final thing that we ask is the following. We multiply by alpha. So here we can have alpha x and alpha y. Is this still an element in S? So this is, in fact, we can write this one. Probably it's best if we put the alpha outside, which means that we are really multiplying with a constant the whole vector. So let's do it like this. So here we have x and y times alpha. We get alpha x, alpha times 2x. This is equal to alpha x, 2 times alpha x. So again, this looks like this is an element of S. So all of these conditions are satisfied, and we could say that S is a subspace of R squared. What can you say about U? Is U a subspace of R squared? Where U is the second line. What can you say?
I think no.
Why?
Because the 0, 0 vector doesn't exist. It's not a
That's true.
part of the.
It's not, yeah, that's correct. So that line, it does not pass through the origin. Okay, so we discard it immediately. So we say that U, sorry, this is U, not subspace of R squared. Simply, but you need to explain it. So you have to say that, okay, this line does not pass through the zero, this line does not include the 0, point, and as such, we cannot even find a negative vector v, so that when we add the vector v with the negative, we'll get this 0w. Okay, that's correct. So in a similar way, even when we had a plane where I think we did this before, we had a plane and we asked whether the plane passed through the origin or not. That's all we could say. Well, that's all we need to consider to get something. Now we're going to define the null space. Null space of matrix A. What is the null space of a matrix A? The null space of matrix A, it is the set of solutions of an equation which looks like this: AX is equal to B. Okay, so sorry, that's not correct. This is the B, but when B is equal to 0. So what is this equation? What do we call this equation? This is the homogeneous equation. We know that when B is different from 0, this is called the non-homogeneous equation. So when AX is equal to B, this is the non-homogeneous. And this terminology of homogeneous and non-homogeneous, you can see this one also in differential equations. So you might see this later, you might say, oh, okay, linear algebra uses an equivalent or similar statement or definition when it comes to determining whether a system is homogeneous or not. Now, so we said this is a set of solutions. Let's try to get a little more, a more common understanding. So A, let's assume that A is n by n. Then what is the vector x? What is the dimension of vector x? How many entries does this have? N by 1, right? So this is what we're trying to we write this in the general form so that we can understand what domain, or this one, is a subspace of which space. So this is AX n plus 1. This is equal to what? 0 vector. How large is a 0 vector?
M1.
N by 1, that's correct, N by 1. So, and now, so what is the null space of A? This is a subspace of R. We see here N, Rn, okay? And I want to ask you something. What is the range? So maybe we can write this again. So it looks like the null space of A. This is a subspace of R, what was it? N. What about the range of A? What is the range of A? What is the dimension of the range of A? Rn. That is correct. Why is this so? Why is the range of A subspace of Rn? Now, when we did the range here today in our class, we said that the range was what? What was the range? It was defined as a linear combination of what? Of the columns of A. Okay, so we combine the columns in one way, and then we obtain the range. For example, it's always good to have an example. We have -1, 2, -5. This is matrix A. 3, 2, -1. 6, -5, 17. This is a matrix A, okay? And then let's see how can we pick up, how can we make a vector which is in the range of A. So someone in the class, let's say, who wants to give me one vector which is in the range of A. I can pick someone myself, Denis Shashori, Denisi. So find the vector B such that B is in the range of A. Denisi, can you answer this? After Denis, we have Drilon. Drilon, Denisi, Emini, başlayalım spas alphabeted. So, among Denis, Drilon, Emil, and Emin, so who can answer this? Then we go to the volunteers. So, in order to determine a vector which is in the range of A, since we are expecting to get, actually we can generalize a little further. Allow me to make this because we might be confused. Let this vector, let's use matrix A, that is B, -7, 1, 8. Okay? So let's make a vector with matrix A, which is 4 by 3. 4 rows, 3 columns. Denisi, do you understand my question? Denisi? Or Driloni? So we are looking for an element which is in the range of A. How can we do it? You just combine these in whichever way you want. So you can do the following. Why don't we do this? C1 plus C2 plus C3, which means that we just add them. Okay, we multiply them by 1, we add them, and we should find the vector B. In this case, B would be equal to, what is this? C1, these are all columns, okay? They are not constants, these are columns. So what do we get here for B? We get -1 plus 3, it's 2 plus 6, 8. 2 plus 2, 4, -5, -1. -5, -1, -6 plus 17, 11. And then we have 9 minus 7, 2. Fine, we got it. So this is the vector B, which is in the range of A. How did we find it? It was a linear combination of these. So it looks like the range of A, this is why this is a subset of Rn. We can find another vector, so we can do the following. We can do C1 minus C2 plus 2 times C3. So this would be another vector. Let's see what we get. C1 minus C2 minus 1 minus 3 minus 4 plus 12, 8. Then we have 2 minus 2, 0, minus 10. Minus 5 plus 1 minus 4 plus 34, 30. And then we get minus 7 minus 1 minus 8 plus 16. What is it? 8. So this is again in the range of the matrix A. So now we have the null space and we have also the range of A. Now, this range of A, we can also define this, we can call this one the column space of matrix A. Why do we call it column space? Because it is equal to the linear combinations of several columns. We can write as a column space of A. The column space of A is what? It's a subset of Rm. Okay? What about the row space of A? Column space of A, it defines the linear combination of the rows. Now, can you give me one element such that, or let me call this was B1. Let's find an element B2, which is an element of the row space of A. We can start. Andy, can you answer this question? Andy, then we have Aneda. Now I'm going to think that my internet is down, and maybe I'm not talking to anyone. Maybe I'm talking to the wall. So who is gonna take me out of this misery? Who can answer this? So who can construct a vector B2 such that the vector B2 it can be expressed as a linear combination of the rows of A?
Minus 11.
How did you make this up? How did you combine the three rows?
Row 1 plus row 2 plus row 3 plus row 4.
That's good. Row 1 plus row 2 plus row 3 plus row 4. So let's see. Tell me the numbers. What were those?
Minus 11.
Yes.
5 and 20.
5 and 20?
26.
23. Okay. So this is 20? 26. Sorry, I cannot hear very well. 26. So this is, what is the row space of A? A row space of A is 1 by 3, right? 1 row, 3 columns. So this is for B2. What would be another vector? So B2 is described like this. We can even have the following: row 1 minus row 2 plus row 3 minus row 4. Okay. So here we have another combination of the rows, or of the row space of A. In this case, another vector B2 would be equal to row 1 minus row 2. We get minus 1, minus 2, minus 3, minus 8, minus 1. And then we have 3 minus 2, it is 1, 0, minus 1, minus 1. And then we have 5, 11, 28, 20. Okay, so here we have another vector, which is 1 row by 3 columns. So I hope this is clear. It is also intuitive. It's not very challenging, I believe. But now that we are discussing the null space of A, how can we also perceive the null space of A? When we look at this equation, AX is equal to 0. Let's try, let me think for a moment. Wait a second. So this part is not including a very fundamental or essential piece of information. We just know B1, B2. So let's take this out for a moment. And let's have a look at this matrix we made up. We are talking about multiplying this one with vectors x1, x2, and x3, right? And we are expecting here, so this is 4 by 3, right? 4 by 3 is a matrix. What is the size of the vector x? 3 by 1. What is the answer vector here? This would be 4 by 1. Okay, then we should get here 0, 0, 0. Now, if this is the homogeneous equation, and we want to find a triplet of values of x, x1, x2, and x3, so that this is satisfied. Now, how can we get, let me ask you this, I don't have, let me see. How can I get this 0? Can somebody help me here? How do I get this 0?
The third row times the column, the x vector.
Yes, row 3 times, or inner product with the vector x1, x, okay? You are correct. Thank you for providing this information. And this is equal to, what is the third row? It's minus 5, minus 1, 17, minus 5, minus 1, 17. We multiply this with x1, x2, and x3. What do we get? 0, right? This is the third 0. And how can we get this other one, this other 0? We do the row 2, right? What is the row 2? Row 2 is 2, 2 minus 5, 2, 2 minus 5 times x1, x2, and x3. This will still be equal to 0. In fact, what are these? What we have here, this is the inner product between all the rows, so we can call this row I times x, and this is equal to 0. This is a vector, this is a vector, and in principle, for any homogeneous equation, which is described like this one in here. So this is our homogeneous equation. All the rows of A, so the row space of A, I call this row I can be from 1 to 4, or 1 to n. If we multiply them with any vector, which is in the null space of A, we get a 0. So let's not forget, the null space of A, it is not always a single solution. Why? Probably we don't have a unique solution. We know that sometimes in our equations we have a line or we have a plane as a solution, which means that we have an infinite number of possible solutions. So we don't have a unique one. In that case, we could pick up any vector in the null space of A. Then this answer could be the following, not answer, this conclusion could be the following. Any element among the rows, let me call this one row space of A, inner product with the null space of A is equal to what? Is equal to 0. Okay? It is interesting. So we notice that the row space and the null space of A, they are orthogonal with respect to each other. So we can write the following. Row space of A and the null space of A are orthogonal. Okay. So we hope we understand what we have here on the board. Do you have any question? Any question for what we did so far? Yes, if you like, Ray, we can have a short break. I'm fine with it. We can have a 10-minute break, and we can meet in a little later. It's just lunchtime. But if you have any question, I can answer, or we can go into the next stage.